right, so we're going to complete um, our mass simulations. Okay, so what we're going to do is first we need to get the correlation. I got to look up the name of the function real quick. Hold on. Correlation function XL. Corel. Okay, so let me make that up. Good, good, good. So you'll see that if we run correlation y2, it knows to skip the NAs. If it doesn't, we can just parse the NAs out. It's not a big deal. To Z. I think actually we're going to be doing Democrats into Republicans. So, but okay. Well, we might have to start this at 3% of the ballots cast. So hold on. Or 6% or whatever. Right. 0.7. I have 0.055. Perhaps Z. Oh, I see. Z into Y. But we are going to be doing the other way around, okay? So 0.747. I still have 0.055. Oh, you know what it is? We have to do... I see what's wrong. We'll do both so I know which one is which. So hold on. Do we go X or Y? Okay. So to just give me both real quick. So let's do... I just want to see both of them. Well, let me calculate. I can't figure out what's going on. Unless I have to put in a constant. Let me think if I have to put in a constant. Let's see something. ADAC, ACAC. Oh, this should be ADAD. My bad. Okay. Hold on. I'm hoping that, because if this is how it's doing it, I don't see how it's doing it without a constant. You know what I mean? There might be a linear correlation function.
Oh, yes, that's right. The enchanted card.
Oh, you know what? It's not giving us. It's not giving us the updated R squared, is it? Hmm. Isn't there a function for this? Hmm. We might have to calculate it ourselves. That would be really sad. That'd also be very intensive because it won't be a native function. I have to sum cell by cell. Oh, I gotta take the square root, I think, or I have to square it. Power squared. There's our 8106. I was like, yo, this don't make any sense, dude. Oh man. That had me a little worried there. All right, so we do have it. So we have r squared 8106, okay? And then the that gives me the same thing, okay? Now all we're asking is, suppose I did this in reverse, okay? AC, AC, AD, AD. And it may just go with, it's possible that this is doing a covariance matrix, which means it's just going to return the highest one of the other. But I'll know after I see the calculation. Because you would think that yeah. Because I know if I go change these axes real quick, we're not going to be using these graphs anyway. We're going to be just calculating R squareds. I'm just trying to figure out why it's not respecting what it is we want to write here. Because look, if I put H before G, right, and then I go graph them, I should not be getting the same R squared value. That would be, to me, very unusual. Not that it can't be. I mean, they almost do imply each other, so it's technically possible. Okay. So it's probably true. Even though I guess it's because it's more of an eigenvector relationship than it is a linear regression in this case, because that's the only thing that makes sense to me. Like, I'll get a different equation, but I think I still get the same R squared. Okay, you know what? Well, then it means we're doing it correctly. Were there any differences here? That's all I want to know. Not really. They're both pretty crappy. And again, I just want to check that. So you're saying if I graph this against this, and I take the R squared value, wherever that may be, and then I took instead this against this, and I also took the R squared value, even though it flips the whole picture, you're telling me that I get the same thing. If it's true, then it has to do with some sort of eigenvector. And I think I'll explain. This is my hypothesis for why, but yeah, it seems to be true. So since these aren't random data points, right, they're a continuous derivative of a function, it could be that each data point technically controls the range in which the next data point can appear. So that'd be cool. So that I think that's causing an eigenvector relationship. But as you can see in the simulation, the eigenvector is 0, but because there's some sort of sequence of ballots being cast, whether it's the actual election or the simulation, that sequence is driving an eigenvector. That's my hypothesis for why we get the same R squared. If you know more about that, just leave me a tell in the YouTube comments. I would like to know more. But unfortunately, I don't have time to probe that issue. But if I had to guess, that's probably the reason. So that's definitely a good place to start your research if you want to answer that question. And like I said, I would love to answer it, but I don't have time to do that right now. All right, so long story short, this gives us our R squared. All right, so now that we have our R squared, and apparently it doesn't matter which one we take, I still want to do Democrat into Republican. So that's going to be AD into AC. And because we're using psi instead of r squared, okay, what we have to get a way to get psi, right? Because XL is not going to calculate psi. Doesn't mean we can't obtain psi from that. So the r squared value is 1 minus RSS over TSS. Okay. Psi is just the ln RSS over TSS. So let's isolate this. So let's do r squared, 1 minus r squared, okay, equals RSS over TSS, which says that psi is equal to the ln of 1 minus r squared. Now, to show you what that looks like in Desmos, okay, and then I'll also go over percentages real quick while we have Desmos open. So we're saying, okay, we have this function y equals x. R squared is going from, doesn't matter where it's going, it just has to be less than 1, okay? So x less than 1. So that's the range of our r squared. Usually it's bounded to 0. We're saying that y now equals 1 minus x, or what? Hold on, let me see. Yeah, 1 minus x, and then take the ln. Okay, so r squared 1, perfection, corresponds with psi equals negative infinity. And now you can see the relationship here, okay? R squared 0, well, means that psi equals 0, meaning it's no better than the baseline average. A really bad model that's akin to just picking random numbers from 0 to infinity to predict the data has a negative r squared, and you have a negative psi, okay? So that's the relationship between r squared and psi. If instead we were to look at it from the perspective of psi, can I get r squared from the perspective of psi? Well, then r squared, okay, is equal to 1 minus e to the psi. So it would be e to the x, okay? So what happens when we do that? Okay, well, now we get y equals x, and now we just get y equals 1 minus e to the x. So you can see that there is in general a symmetry, because now we're saying this is r squared. Sorry, this is psi, and this is r squared. But from the perspective of r squared, this is r squared, which is bounded at 1. It can't go beyond 1. And that's the problem, okay? And this is still a hyperbola. So comparing the models, this is what you get. In some ways similar, in some ways not at all. Okay? Whereas psi can go anywhere from 0 to infinity, and r squared can go anywhere from 1 to 0. 1 to negative infinity. But psi can go from positive infinity to negative infinity. because r squared can only go from negative infinity to a artificial boundary made by humans of 1. Okay, so that's that. How about percentages real quick? Well, here's your percentage going from 0 to 1, right? I like to do this for people. That way they see the boundaries. So all your percentages exist inside of this little black box. Okay. Well, the equivalent in vote ratios, I'm going to call that Y1, is X over X minus 1. Okay. So when you have 50% of the vote, you have a 1-to-1 ratio. If you have 75% of the vote, you have a 3-to-1 ratio of votes. So the advantage of the percentage is that it's symmetric based on ratio, but the ratios themselves are not symmetric. So ratios are going from 0 to positive infinity, sort of like r squared having an artificial boundary, but still going to infinity in the other direction. And percentages, they have 2 boundaries, but at least it looks like a straight line. You think it does, but it's not. So then the real thing that you would want to graph then is y3. You want the logarithm of that vote ratio. Okay. I'm going to put a scalar here. That all that does is change the log base. Okay. And now you have a nice symmetric. You have something that is symmetric and unbounded in respect to the percentage. But is that really the correct way to look at it? Well, no, you should actually look at things from the perspective of an observer in logarithmic space to see how this really looks, okay? So here, once again, we have y1. And now we're saying that this goes from 0 to infinity. That this is going to be our logarithm. The x-axis is now a logarithm. Okay, then I want to get that ratio, right? So y2, it becomes the ratio here. I have to write y22 equals e to the x, e to the y1. Okay, so this just became our ratio. And you can see that the ratio now has symmetry in respect to the line y equals negative x, okay, in a weird way, but you have to also add 1. Okay, and now we want to go get our percentage. The percentage form is going to be y33. Well, that's equal to 1 over 1 plus y22. And that, my friends, as you know, goes from 0, 100%, to 1. Do we mean to put 1 minus here? The logarithm is 2. Then would that be... Oh, this is cotan. Alright, so hold on. This is cosine over sine, which is cotan. 1 plus cotan is cosecant. So I have to put 1 minus. Okay, there we go. All right, so we're going from 100% to 0. Okay. 50% occurs right here. We can get rid of these boundaries now. They're artificial. Okay. And just to like sort of normalize this, okay, I'm just going to take the whole thing and just subtract one more from it, 50%, okay? So you have this object that is, if you get really deep into it, it's the equivalent of an arctangent function. In fact, the way I'm producing these identities is by doing 1 plus cotan squared, which is cosecant squared, then taking the reciprocal, and then doing 1 minus to get cosine squared, okay, or whatever. And, you know, this is real. I think it's hyperbolic arctangent, but you get the idea. Like, you can figure out those identities if you want. So from the perspective of logarithms, in logarithmic space, the percentage behaves quite linearly for the beginning, right? This is why if this is normally distributed in the average, if you have a 1-to-1 vote ratio on average across the precincts, it means you have like a 50% split, then that's, since this is semi-linear in this range, if the logarithms are normally distributed, which they usually are, the percentages will also be normally distributed. But over here, when, you know, somebody's getting 90% of the vote, on average, like in a blue city where Democrats get 90% of the vote, you don't really get means and standard deviations anymore. You're completely cut off when it comes to percentages. But logarithms, they just keep plowing on. Okay? All of this stuff matters. I'm not just talking about this and lecturing about it for fun. It really matters. You have to understand how to change reference frames. So when I say the x-axis is the logarithmic, is the ln of x, well, that means that from another observer's perspective, the axis looks like this. Just e to the x. But there's another observer who perceives this purple line as a straight line that's just linearly increasing. This is actually called the concept of the moving observer. Okay. There's, you know, take x squared. Well, there's an observer who sees x squared as the x-axis itself. We know this is true because multivariate least squares regression treats each variable, like in a polynomial regression, as if it's its own linear axis, even if it's actually not linear. Now, to continue this discussion, I have to talk about something called axial density, where the density of an axis is equal to the derivative of the function that the axis represents. So the beauty about the logarithmic axis, e to the x, when then put into a straight line form as the regular x-axis, says that the derivative of e to the x is e to the x, which means that the density of the axis is increasing as e to the x. Right? It's its own derivative, its own integral. Anyway, let's go back to mass simulation. Just wanted to give you this overview. All right, so we're going to delete these graphs. We know it works. Okay, we got to do the thing. To get r squared, we know we have to do the ln of 1 minus r squared. Okay, so let's do that here. This will give us psi. So the ln of 1 minus r squared. Very good. And then over here, very good. Okay. So now I'm going to save this. In case, something goes wrong, we can always come back to this version and start over. And now we're going to be getting rid of everything we don't need. Every single thing we do not need. Okay? We don't even need the actual election in the simulation action. The only thing we're going to be taking from that is its psi value. That's the only number I need from the whole thing. While that's loading. Alright, the vacuum cleaner's going, so I'm going to pause this video for a moment. Alright, so let's proceed to mass simulation. Now we're going to do save as. I'm actually going to, this is my first time doing this, so I'm actually going to put in my real folder here. Nevada, Clark, General, Simulate Mail, RCV, Ranked Choice Voting, okay? So, when we do mass simulations, we have to get rid of every single column we do not need. Since we already have what's it called? The probability distribution array hard-coded into the simulation. We don't need that, okay? So we don't even need the precincts page or anything. For my own record, though, I'm just going to leave this. So, like, technically we would delete this. It's not a very large page. So, I mean, I guess it can sort of stay there, okay? You might notice that there's a few precincts where we're going to get divide by 0 errors. So we do have to deal with that issue, okay? Before we proceed. And that's in the probability distribution array itself. And that will happen simply because the precinct didn't really have that many votes in it. Like, you have, like, no votes in this precinct, blah, 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 blah. Although, I don't think it was affecting our ability to grab a correlation coefficient, was it? Oh, you know why? Because all those precincts are redacted in the cast vote record. That's why. So we got away with murder on that one. Basically, our Boolean function, Boolean 5, took care of that for us, but you don't always get that lucky. So thankfully we won't have to deal with that in this simulation. I think we would just set up if error is 0. Yeah, we'll do that for safety. Let's just do that for safety. So the only thing I do is if error, the function, 0, okay? And then everything is fine. If error, the function, 0. Okay. Leave that there. Delete. shouldn't be doing this. That should have loaded right away. I'm not liking that. Hold on. Thank God we saved this. Alright, we're just going to have to pray to God. Thank God. Thank God we saved it. I'm not liking that. Listen, if error, we get a 0. Boolean array 5 already handled the problem. Okay. Alright, so what don't we need? We don't even need the precinct number. We don't need this. We don't need this. We don't need cast vote record number. I don't even need the operator. I don't need anything. We know what all of this stuff is. Okay. Let's go ahead and delete it. Do I need time? Well, no, I'm not graphing anything, right? We can get rid of that. So this is all the columns we need to do this. And then we get this psi value right here. Okay. Now before we start making copies of this spreadsheet, what we need to do is we're just going to set up an array, okay? So we're going to get our values, and they're going to pop out here. So for instance, this is going to pop out here, okay? And then I don't think we can handle more than 16 at a time. We'll deal with this in a second. And we're going to be copying and pasting per 16 set of simulations, okay, into an array. So I know from experience that you need at least 1,024, sometimes up to 4,096, okay? So if we're doing 16 simulations at a time, okay, we're going to have to do a total of 256 manual simulations, okay? So let's do... by 64. 16. 256. So we got to create a box that's 16 by 16 in a weird way, right? So we can probably fit, if we zoom out, can I at least get 64 of these? I can, okay. So then I'm going to need 64 columns. Let's try to break it up into smaller chunks. Let me see. What's the original number again? 4,096 is as far as we're going to be going, so... let's divide that into... 16 by 16. Is that what we want to do? Yeah. Okay. definitely recommend color coding before you do this. It will save you a world of hurt. Okay. So we're going to create 16 boxes at a time. Okay. So 16 by 16. Then And then when we're done putting these in to all these boxes, okay, all we have to do is get rid of the rows between them and stuff. Yeah, so we get rid of the extra columns and rows, and then we just have all these psi values. And then we go and get the mean and standard deviation, okay? So what I usually do for this, it's not too different than what I normally do to begin with, is I do one box at a time, just like this, okay? So you get the general idea. Oh, need a few more. But here we don't need anything, so we'll just get rid of this. Okay. And then when I finish this, I paste it into one of these, whichever one needs to be filled. Okay. That being said, we have to go set up a whole bunch of simulations. So we don't need this sheet. I'm actually going to get rid of it. Okay. The only thing I need from this sheet is this. Okay. Whatever this value is, it's the only sheet I need here. Okay. I'll pick that value up in a moment. So this is the actual election psi value. Okay. Okay, now that. Alright, now the simulation, we're just going to call it S. You're going to put parentheses 0. Okay. And the only thing we're picking up off of this is the ln of 1 minus r squared. That's it. That's the only cell we care about in this whole thing. In fact, what we're going to do is put it over here in cell A1, because by putting an R column, Excel starts wondering in its memory if I have other stuff here, even though it's blank. Okay. Now let's go ahead and save. Okay. What we're going to do now is remove all cell formatting. So select the whole sheet, automatic. Okay. This will be well worth it. No fill. Anything that we can get rid of, we're getting rid of. Everything goes. No border. Oh, when we do the S0 name, we actually got to put a space. So hold on. S space parentheses 0. Okay. Save one more time. And you'll see the saves 10 times faster. All of a sudden, it's like there's nothing in the spreadsheet. Okay. So all the formatting in Excel actually causes a lot of bloat. Since the formatting did its job, it helped us visually navigate the spreadsheet. We don't need it anymore. We know that A1 is the only value we care about in this whole spreadsheet. Close it and then reopen it. Okay, I'm going to reset my RAM.
You just check it. Like it won't pick up.
Yeah, it stops.
Yeah, it's not.
Okay, so now that we have this, okay, we now need to start making copies of this. Okay, so this is pretty nasty. Create a copy, move to the end. And we're just going to keep doing this over and over and over until we get to S parenthesis 15. When you do this, make sure you're on manual calculation. Otherwise, this will be the nastiest process you ever endured. I will also not be saving the spreadsheet from here. If we crash, we have to come back to sheet 1 and start over. Okay? Simply because the amount of memory it takes to save 16 copies of the same sheet is 16 times the amount of memory. Whereas every time I complete a block, I'm going to probably put that in a different spreadsheet file. Okay? Whatever you do, do not copy more than one at a time. If you copy 2 or more sheets at a time to try to save time, you usually waste time. So I'm going to pause this until I get all 15 sheets. Okay, we want to test this real quick at 8 simulations, because there are a lot of ballots here, right? It's about 500,000. So as soon as this is ready to respond, we're going to go ahead and hit calculate once. And based on how long it takes to respond, I'm going to know if we can actually go up to 16 for a file this large.
So let's hope it goes. Me too. All right, so I'm gonna finish it. Thank you. Thanks for understanding, because it's my.
Here we go.
Yes.
No, the answer is we cannot go up to 16. You can tell here how long it's taking to load. So we're only at 15% of the calculations. So 15% means it only did 1 sheet, right? 25% means it now completed 2 sheets. 50% is 4 sheets. 75% is 3 sheets. So we will not gain any performance from going up to 16 simulations. And all we do is risk crashing the program. So we stop at 8. So it's still the computation is fast enough that I'm okay with actually saving this file. So I'm going to go ahead and do that. And then all we have to do is just set our compiler sheet to pick up the psi value on each of the simulations in cell A1. Nasty process, huh? So we have to do 8. So hopefully we don't need that many simulations, because that means I have to render this 512 times. So, 512, well, it is what it is. Divided by, I'm going to be sitting here for 8 to 9 hours tonight. So, it sucks, but it's what has to be done. So let's pretend we had finished this, okay? When we compile our psi values, we're probably going to get some sort of half-folded distribution. So to undo that, okay, we just take all of our psi values when we're done and add them to an identical list of their negatives, okay? And since the r squared values are low, therefore the psi values are low, like they're close to 0, we may have to take the square root as well. If I do have to do that, it'll be notated in the documentation. So I'm going to finish setting up the simulation here on video and just show you basically what this would look like, okay? So S1, S2, S3, S4, S5, S6. We're going to have S7. Okay. What does it mean? Okay. S1, S2, S3, S4, S5. Now, Sometimes for something called a hyperbolic residual test, we're just looking at percentages. Wow, what the hell was the number? 6. We'll have like, well, actually, we're usually able to go up to like 1,000 simulations at a time. In that case, we actually use a code to write the thing itself. To even write the cell formulas, but thankfully, we don't have to do that today. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay. And now this is really it. So you can do it this way. You can also do it. Let me pop this out real quick. Control Shift V will also paste values only. Really doesn't matter what you do. I like to do this into Control Shift V. Right? Then pretend we kept doing the simulations. You fill them up. I'm just filling this up for the sake of the argument here. Just pretend these are all different for a moment. Then this all gets filled in. Then you go bring this over to this block. Since this is not as large a file as I thought, every time I complete a block, I'm going to go ahead and save it. Okay. So I'm going to stop the video now because I don't think you want to watch me sit here for 19 hours. So whatever it is, 8, 9 hours doing this. This is why I can't be in every courtroom in the United States prosecuting election fraud. Things take time, you know? Alright. So, the other tip, of course, is to just put on auto calculation. And every time you copy and paste, it will dynamically regenerate the whole thing. And then do whatever you gotta do. Come back, boom, boom, boom. Paste the next one. Watch Netflix. Paste the next one. Watch Netflix. Paste the next one. So that's what I'm gonna be doing for the next 8 hours. Alright, I'll see you all later. Thank you. Oh, I should probably cover the last thing. Once you have the mean and standard deviation of psi or the square root of psi, depending on what had to be done, you keep doing the simulations until the distribution of psi and its negative component. It's very important. And its negative component passes a Shapiro-Wilk test, okay, which you can get online. You can just pop it in. And I always forget the name of the other one. Anderson-Darling test. So you want it to pass both tests. Now, yeah. So the data and its negative gives you a perfect normal distribution, or the data itself just gives you perfect normal. That might be fine. You may not need its negative. But sometimes you get half-folded distributions. It'll be pretty obvious if you do. So just remember, if you do, to replicate your data points, append them to a list with their negatives, and then run the tests on them. Once it's normally distributed, which I guarantee this will be because I've done many of these before, then you go calculate the sigma value of the actual election. That's it.